So good morning, everyone, and welcome to this third webinar on statistics. So yesterday we have been looking at energy statistics by commodity, and today we will go even further and look at how we can use the commodity balances and create and build the energy balances and then the CO2 emissions. So this is the agenda again, as a reminder. So today we are on the third session on energy balances and statistics, and tomorrow we will do the last of the fourth statistics session on energy prices and energy efficiency indicators, followed by then from next week on modeling sessions. Before we start with the technical part, let's quickly look at some of the housekeeping rules to make the sessions the most effective. So the whole session today, it's virtual. If you have any questions, please use the question and answer box and let us write down your questions, and we'll either answer them live or through the Q&A box. If you have any urgent clarification, you can also raise your hand. And if you have any further questions on energy statistics or balances, you can write to me or to Arnaud or to the Africa program mailbox. So today, this is the agenda for this session. We will look at this presentation. It will be divided into 5 parts. And first, we will see what is an energy balance and how it differs from the commodity balance, and also how the IEA energy balance is constructed. Then we will see also the importance of calculating an energy balance and the advantages you can derive from it, such as generating indicators for analysis and CO2 estimations. We will also study the principles of creating an energy balance. We will look at the IEA methodology and also the definitions used with a focus on calorific values. Then I will show you how an IEA energy balance looks like and how the transformation of energy happens within the balance. And finally, we will see how, with the data from the energy balances, we can calculate the CO2 emissions from fuel combustion. So let's get started. So the energy balance, it's a presentation of the basic supply and demand for all fuels in a manner which shows the main fuels together, but separately distinguished and expressed in a common energy unit. And the energy balance, it takes the form of a matrix where columns present all the different energy sources, that is products, categories, and the rows, they represent the different flows grouped into 3 main blocks: energy supply, transformation, and final consumption. And to develop an energy balance from the set of commodity balances, there are 2 main steps. First, you have to convert to a common energy unit, and then you have to do some reformatting in order to avoid double counting. And we will look at this in more details later in the presentation. So this format, it allows the easy comparison of the contribution of each fuel that each fuel makes in the economy, and also their interrelationship through the conversion of one fuel into another. So with an energy balance, you can really get the global picture of the energy situation in the country. And another way to present an energy balance, it's through the Sankey flowchart, which is a graphic format. It is exactly the reverse matrix that we have seen before with the products and flows, and it gives you a quick visual picture of the energy sector of the country over time. So the arrows, it shows the energy flows from production on the left side to the final consumption on the right side. You can see here that flows, they can be combined, splitted, and traced through a series of events. And the width of the arrow, they are proportional to the flow quantity. I really recommend you to go on the IEA website. So you have the link here below, and you can really look at the different Sankey flow charts for the different countries of the world. And you can use also the timeline to navigate from 1971 to the latest year available. For the moment, it's 2018, but in August, when we will publish the 2019 data, it will also be updated. So this is the Ghana, I'm sorry, this is the Ghana Sankey flow chart. And here you can see with just a visual, very quickly, you can see that here oil is one of the major fuel in the economy, and you have a big oil production, and most of it is exported. And then you have some oil products that are imported, and then it's mostly used in the transport sector. You also have some biofuels and waste productions that is used first for to be transformed into other products, for maybe charcoal, and then you have the biofuels and waste that is consumed directly in the in other sectors, such as residential sector. You can also see that in Ghana, we have some hydro production as well, some gas production and imports as well. So really, just with a glance, you can really see what are the main fuels in the economy, which sector, final consumption sector, consumes what fuel, and it's really useful. Before we start with the presentation, let's quickly do some Menti question on energy balances. So I will now share the Menti question. So please connect to www.menti.com and use the code that appears up, which is 36, 29, 23, and 32. So please connect to the Menti website and use the code 36, 29, 23, and 32. And the first question is it possible to have a statistical difference which is equal to 0 in a statistics table, which is in physical unit, and which is not 0 in the related energy balance? So for example, you have your statistics table for coal, which is in kiloton in physical unit, but then when you convert it into an energy balance and you report it, for example, like at the IEA, we use ton of oil equivalent, is it possible to have a statistical difference? And when we say, is it possible here, we are really thinking about the methodology and definition. Think about, is it if you did not have it in the physical unit, should you have it in the energy balance? So there are 10 participants that have replied. 8 think that yes, it's possible and it's normal. It's mostly this: is it normal to have a statistical difference that is 0 in statistics table and not 0 in the energy balance? Technically, is it possible, yes or no? So in an ideal case, when you don't have a statistical difference in physical units, you should not have it also in the energy balance. But it's possible to have it because sometimes you have issues on calorific values. You might have data which are misreported, and so it's possible to have it in the energy balances. Next question is, in an energy balance, you see a positive number in the total column of a transformation flow. Is it possible? So here, let's take, for example, oil refineries transformation. So you have an input of crude oil, and then you have an output of oil products. And in the total column, you have a number there, which is usually the sum of the rows, which is the input and the output. Is it possible there to have a positive number, knowing that in the transformation sector, the input is a negative number and your output is a positive number? So when you sum the two, and you might get a positive or a negative number. So is it possible to have a positive number here? So here there's 3 possible answers. Yes, it means that the transformation efficiency is very high. No, transformation output are always equal to the inputs and totals are always equal to 0. Or no, totals are always negative because transformation efficiencies are always lower than 100. So think maybe of this example I just gave about oil of refinery transformation. You have an input of crude oil, an output of oil products. Is it possible to have a positive number in the transformation? And here we are talking about energy balances and not energy commodities. So we have 13 participants that have replied, and 8 think that yes, this means that the transformation efficiency is very high. No, totals are always negative because transformation efficiencies are always lower than 100. And the correct answer is the last one. So no, it's it's technically it's not possible to have more output than input in energy terms. And no, logically, your efficiencies should always be less than 100. In commodity statistics, it could happen in physical terms that you have a bit more output than input, but in energy terms, you cannot produce more energy than what you're inputting. And if this, it is possible that in energy balances that we receive at the IEA, sometimes we do have this positive number here. And here, usually we contact countries, we try to investigate if the numbers have been reported properly. Sometimes there could be errors in the input or the output, which leads to this over 100% efficiency. So that was it for the Menti question. And now let's start with the presentation.
Now, let us see in more details the importance of calculating an energy balance and what you can derive from it, such as generating indicators for analysis and CO2 estimations. The energy balance is a way of reporting energy data in a common unit and with products aggregated by category. It has many benefits and uses. By presenting all the data in a common energy unit, the energy balance allows users to see the total amount of energy used and the relative contribution of each different source for the whole economy and for each individual consumption. It also allows comparison of the shares of each source in the energy supply of a country and in each sector of economic activity. Different countries can be compared when they are calculated with the same methodology. With an energy balance, you can develop various aggregated indicators such as consumption per capita or per unit of GDP, and to estimate CO2 emissions from fuel combustion. A country can determine its dependence on energy imports or exports. With an energy balance, it is possible to analyze energy efficiency. The statistician also uses the energy balance as a high-level check on the data accuracy, as large statistical differences in energy units, apparent energy gains, or large losses in transformation processes may all indicate underlying data problems. Also, it allows us to have a good basis for making forecasts and projections to achieve climate goals and to check that policies in place are well implemented. If you want to exploit the full potential of an energy balance, it is recommended to combine energy statistics with economic indicators. These new aggregated indicators allow us to understand how energy impacts society and economy. For example, we can calculate the energy intensity and self-sufficiency of a country. Energy intensity is a measure that is often used to assess the energy efficiency of a particular economy. The numerical value is traditionally calculated by taking the ratio of energy supply to gross domestic product, indicating how well the economy converts energy into monetary output. The figure on the left side shows us how primary energy use and GDP have changed globally over time relative to a normalized year of 1990. As you can see, GDP and total energy supply are decoupling, and this can be due to several reasons such as structural changes and efficiency improvement. In sub-Saharan Africa, the energy intensity is decoupling less quickly than globally. Obviously, low energy intensity is the desired goal because it represents an efficient allocation of energy resources to generate wealth and a high quality of life. So it is logical to expect energy intensity to increase and for GDP and energy use to be closely coupled during the initial stages of development of a nation, since the early years of access to electricity and utilization of more abundant energy includes many energy-intensive activities. The developing economies will need to produce a tremendous amount of cement for roads and buildings, as well as steel for automobiles, appliances, and telecommunication infrastructures. These will be new users, some of which will naturally be energy intensive. We can also compare countries to see where each other stands for. In this graph on the right side, you can see that OECD countries are less energy intensive compared to non-OECD countries for the reasons I mentioned before. In sub-Saharan Africa, the differences between countries are quite large. Some countries, such as Democratic Republic of Congo, is more energy intensive compared to Ghana. Another indicator is self-sufficiency. The energy self-sufficiency rate is the ratio between national primary energy output and consumption of primary energy in a given year. This rate may be calculated for each energy types or overall for all types of energy. A rate of over 100% indicates a national production surplus in relation to domestic demand and therefore net exports. For Africa, if you remove biofuels from the energy mix, then the self-sufficiency declines a lot. In sub-Saharan Africa, a very high self-sufficiency rate is due to the top oil producers. Now, if we compare the self-sufficiency by country, we see that again there are differences because of biofuels and waste. For example, for Uganda, the self-sufficiency can seem very high at around 90%. But if we look at the energy balances, we see that there is a very high share of traditional biomass in the energy mix. And if not accounted, we see self-sufficiency drastically decreasing to 16%. Conversely, for Nigeria, who is a strong oil producer, self-sufficiency even increased because most of the oil is exported and biofuels consumed domestically. However, concerns for oil producers in Africa are on the midstream infrastructures, namely refinery, and countries will indeed import most of the finished products beside a large national oil production. In the case of Ethiopia, if we remove biofuels from the self-sufficiency, then Ethiopia is producing only 20% of its energy demand. Another indicator is the residential consumption per capita. So how much are we consuming at home? In this chart, we can see that the difference between OECD countries and sub-Saharan Africa is quite large. In sub-Saharan Africa, we consume 50% less energy in residential sector compared to OECD countries. However, traditional biofuels used in sub-Saharan Africa is quite large and inefficient, and the useful energy consumed per capita is much lower. This is how the picture looks like if we exclude solid biofuel consumption, which is very inefficient consumption per capita in sub-Saharan Africa. We see that the gap with the OECD is even higher and consumption per capita is very low. Now, let us look at the methodological assumption underlying energy balances. As you know, energy data are generally collected independently across different commodities. To develop an energy balance from the set of commodity balances, there are two main steps. The first one is to convert the natural units in the different commodity balances, that is for coal, oil, gas, renewables, and electricity, to the chosen energy unit. Here it is kiloton of oil equivalent in the IEA balances, but many countries use terajoules. By multiplying by the appropriate conversion equivalent for each natural units, which are calorific values. The second step is some format changes. We need to do some reformatting in order to avoid double counting when summing all products. We need to rearrange the converted commodity balances along one another, rearrange certain of the rows, and introduce a sign convention in the transformation sector. What is a calorific value? It is the amount of heat obtained from one unit of the fuel, and it is the only way to convert a fuel quantity from natural units, that is mass or volume, into energy units, that is kTOE. It is very important to collect good quality calorific values in addition to good data in physical units. As you can see, in this commodity balance, there is no statistical difference. But when we convert to the energy balances using calorific values, then a statistical difference appears. Why? If we look carefully at the calorific values in the middle table, you will notice that the calorific value for the input to electricity and consumption is different from the production and imports. This is something to query with the country. So as you can see, calorific values can be a good check for data quality control. Now, let us look into more details at the principles of an energy balance. The main methodological choices underlying energy balances that can differentiate the final balances layout across organizations are as follows. The IEA energy balance methodology is based on a common unit of account and on the calorific content of the energy commodities. The IEA balances are expressed in terms of net calorific value. The change from the original units to tons of oil equivalent implies choosing coefficients of equivalence between different forms and sources of energy. When constructing an energy balance, it is necessary to adopt conventions for primary energy from several sources, such as nuclear, geothermal, solar, hydro, wind, etc. For each of these sources, there is a need to define the form of primary energy to be considered. There are essentially two methods that can be used to calculate the primary energy equivalent of these sources: the physical energy content method or the partial substitution method. Also, temperature adjustments made by countries should also be taken into account. And finally, we have to know if the balance is based on a fiscal or a calendar year basis. First, we have to choose an energy unit. Then we have to choose the energy unit. It can be any energy unit. It can be British thermal units, ton of oil equivalents, joules, watt hours. The unit of account adopted by the IEA is the ton of oil equivalent, which is defined as 41.868 gigajoules. This quantity of energy is within a few percent equal to the net heat content of 1 ton of crude oil. The conversion of the IEA energy balance to any other energy units would be straightforward. The choice of the ton of oil equivalent is based on the history of the IEA creation after the first oil crisis. The difference between the net and the gross calorific value for each fuel is the latent heat of vaporization of the water produced during combustion of the fuel. This heat is lost and cannot be recovered. For coal and oil, the NCV is about 5% less than the gross. For most forms of natural gas and manufactured gases, the difference is approximately 10%, while for electricity and heat, there is no difference as they are not combusted. The use of net calorific values is consistent with the practice of the statistical offices of the European Communities and the United Nations, and most importantly, it represents the useful energy. Generally, the IEA adopts country-specific, time-varying, and for some products, flow-dependent net calorific values supplied by national administrations for most products. For coal, the IEA has adopted specific factors supplied by the national administrations for the main categories of each quality of coal and for each flow or use. For natural gas and crude oil, specific factors have been used for production, imports, exports, and electricity generation based on consultations with experts from the national administrations. In the case of oil products, the IEA applies regional calorific values. So now we know how to convert combustible fuels in energy units, but what about nuclear, hydro, and other renewables? Why is it so important to compute this input, the primary energy equivalent? Because it is important to quantify the primary energy supply in order to calculate the total energy supply. A very important methodological choice is the definition of the primary energy equivalent for the electricity and heat produced from non-combustible sources such as nuclear, geothermal, solar, hydro, and wind. The information collected is generally the amount of heat and electricity produced, represented in the balance as an output of the transformation. Conventions are needed to compute the most appropriate corresponding primary energy input to the transformation, both in forms and in amount. For each of the following sources, that is nuclear, geothermal, solar, hydro, wind, tidal wave ocean, and solar PV, there is a need to define the form of primary energy to be considered. For instance, in the case of hydro energy, a choice must be made between the kinetic energy of falling water in the turbines and the electricity produced. For nuclear energy, the choice is between the energy content of the nuclear fuel, the heat generated in the reactors, and the electricity produced in the nuclear reactor. For solar photovoltaic electricity, the choice is between the solar radiation received and the electricity produced. The principle adopted by the IEA is that the primary energy equivalent form should be the first energy form downstream in the production process for which multiple energy uses are practical. The application of this principle leads to the choice of the following primary energy forms: heat for nuclear, geothermal, and solar thermal, and electricity for hydro, wind, tidal wave ocean, and solar photovoltaic. We have now identified the form of the energy input, but now we need to quantify it. There are essentially two methods that can be used to calculate the primary energy equivalent of these energy sources: the partial substitution method, which at the IEA we do not use anymore, and the physical energy content method. The physical energy content method uses the physical energy content of the primary energy source as the primary energy equivalent. As a consequence, there is an obvious link between the principles adopted in defining the primary energy forms of energy sources and the primary energy equivalent of these sources. For instance, in the case of nuclear electricity production, as heat is the primary energy form selected by the IEA, the primary energy equivalent is the quantity of heat generated in the reactors. In the absence of country-specific information, the IEA estimates the primary energy equivalent from the electricity generated by assuming an efficiency of 33%. This is derived as the average efficiency of nuclear power plants across Europe. For geothermal electricity, the primary energy equivalent is the quantity of heat, and a similar back calculation is used when the quantities of steam supplied to the plant are not measured. So assuming a thermal efficiency of 10%. This figure is only approximate and reflects the fact that the steam from geothermal sources is generally of low quality. If data for the steam input to geothermal power plants are available, then they are used directly as primary energy equivalent. Similarly, for solar thermal plants, the heat supply is back calculated assuming a 33% efficiency of conversion of heat into electricity, reflecting relatively low working temperatures, although central receiver systems can reach higher temperatures and therefore higher efficiencies. In the case of hydro, wind, and solar PV, as electricity is the primary energy form selected, the primary energy equivalent is the physical energy content of the electricity generated in the plant, which amounts to assuming an efficiency of 100%. So when the primary energy form is heat, we have losses. Let us see a few examples to illustrate this concept. For wind, as we have an implied efficiency of 100%, so with 1000 TOE of electricity produced, the primary energy equivalent is 1000 TOE of wind. In the case of nuclear, as the implied efficiency is 33%, so for 1000 TOE of electricity produced from nuclear, the primary energy equivalent is around 3000 TOE of nuclear. In the case of geothermal electricity, as the efficiency is 10%, so for 1000 TOE of electricity produced from geothermal, we need 10,000 TOE of geothermal. For geothermal heat, the efficiency is 50%. So for 1000 TOE of heat produced, we need 2000 TOE of geothermal. Now, let us look again at the energy balance in tabular format and how to read it. These are the key elements to understand in an energy balance. We have three distinct blocks. The top part, which is the energy supply block, the middle part, which is the transformation and energy use part, and the last block, which is the final consumption. The last two blocks are what we refer to as demand. Only production of primary products are shown in the production row in order to avoid double counting. Secondary products are shown in the transformation block. That is why for oil products and electricity, the production cell is 0. The total energy supply row allows users to see the total amount of energy used and the relative contribution of each different source. Do you think this country is producing oil products? In the transformation block, there is a sign convention. Negative values represent an input and positive values represent an output. Transformation losses appear in the total column as negative values. In the total final consumption block, you have all the different sectors consuming fuels such as industry, transport, residential, and non-energy use. In this table shown in this slide, the energy balance is cut. That is why in the total final consumption, you are seeing only industry, but the table continues. As all fuels are reported in the same unit, then we are able to compute the total products column. In the transformation sector, the negative value in the total cell represents losses of the transformation process. I hope that this presentation has helped you understand some of the dynamism of the energy balances. Here are some key takeaways from the balances. Good energy balances are a compact source of energy information and is very convenient to use. However, a good energy balance requires good quality statistics, and not only in terms of data, but also calorific values. It also enables statisticians to run accurate checks of energy statistics, such as efficiencies, losses, etc. Also, they are the foundation for basic energy indicators, energy account, CO2 emissions estimates, and for modeling.
So thank you for listening. We have been joined by Alexandre Bizel, who is an expert on energy balances. And please, if you have any questions, write to it in the Q&A box, and Alexandre and I, we will answer you. For the moment, there's no question yet.
Hi, Zakia. Hi, everyone.
Hi, Alex. So I hope that this presentation on energy balances has been useful to you, that you have learned a bit about the different concepts and methodologies underlying the IEA energy balance layout. And yes, please let us know if you have any questions on what you have just seen in the presentation. No questions? Don't be shy. I would be interested in knowing if you're familiar with reading energy balances, if you use energy balances in your work. And I think that there's a first question about export. So I realized that export was negative in the table. Can you please explain? So Alex, do you want to take this one?
Yeah, so that's a good point. So we're talking here about sign conventions. In the table here, the production is always positive, the imports are positive, and the exports are negative. So by using this convention, when you sum all the flows at the beginning of the table, it equals what is the domestic supply in the end. So let's say this is just the convention, so as all those flows are directed as an import to a country, so this export is a negative export. So we may think of something where the exports may be positive, but then you will need to switch it to a negative sign at some point. But how it accounts in the statistics are imports are positive, exports are negative in the balances. And so when you sum everything, just by summing the two flows, you have the net import.
Yes, exactly. In the energy balances, in the table, you want to put as positive what gets in the economy. So exports, it's getting out. So that's why it's with a negative sign. Same, we apply the same convention for stocks as well. So if you're building stocks, then it's not what's going to be available to the market. So it's with a negative sign. But if you're drawing from your stocks, if you have a stock draw, then you're adding this amount to the market. So this is with a positive sign. So that's the convention on the supply side. And we also have bunkers there on the top part, where also we apply a negative sign there. There's a few questions that have been arriving. So let me take, what will require for the validation of calorific values for the same energy items in the same country over a period of time?
So not sure here
Yeah,
what.
I'm trying to understand the question as well. What will
Not sure why the
require?
question here. If the question is how to
Check for
understand, it's how
calorific
to build the
values?
time series for the calorific values, maybe. The
Maybe.
calorific values are usually so measurements whenever available, and if not available, there can be some default calorific values as the average calorific values of a region. So how to validate past calorific values? Not easy to answer. They usually come whenever there are measurements, and if not available, we'd use default values. I don't know if it was really the question.
So we have some ranges for calorific values. So a way to check that your calorific values is correct is to check if it falls within the ranges. And also another way to check is that usually calorific values, they should vary over time, but very often companies, they report the same calorific value for multiple years. So there are a few ways to validate your calorific values that are submitted to you. And also it depends on the, for example, for coal, there are various types of coal. So depending on the quality of the coal, the calorific value depends, is lower or higher as well. So for example, lignite has a lower calorific value than bituminous coal. So I don't know if we answered the question properly, but if not, please write, let us know.
The calorific values are usually not subject to major changes through years. I mean, the different calorific values are mainly structural for structural reasons. So what kind of fuel is used is in coal power plant, for instance. So it doesn't vary much through years.
Yeah.
So this is
But
not that type of accuracy, which is really important, but more to understand, in general, the calorific value of the fuel used in the country. And then if it cannot be refined year on year, yeah, I would say it's more structural than really important.
Yeah, but sometimes you might be changing, for example, importing from a different country. So then normally the calorific value will change a bit. So it really depends, I think. So why is efficiency for hydro, wind, and solar PV 100% in the slide calculating the primary energy equivalent for non-combustible sources? Is that different from the conversion efficiency? You want to take this one?
Yeah, so on hydro, wind, and solar PV, we are using the physical energy content method here, which means this is a convention again. This is a choice. So as the primary energy produced in hydro, solar PV, and wind is considered to be equal to the electricity output. So this is not actually the wind, for example, in a wind turbine. We don't measure the energy that comes really into the blades before reaching the electricity, because this is something that cannot be measured first easily, and that has no statistical meaning. So we start from the electricity output, which is usually the only output that is usable in those sources of energy. And this is allocated with 100% efficiency to the relevant production flow. So wind, solar, and hydro. This is because this is the closest meaning in terms of physical terms. There is no point really to put here another efficiency, knowing that this primary energy cannot be used for anything else than producing electricity.
Yeah, so for those, as electricity is the primary energy form, so here there's no losses. Yeah. Next question is, how do we account for the statistical differences when modeling national demand and supply? For example, when modeling in LEAP. So here, what I know that we have been doing in the World Energy Outlook, when we model energy demand, so for statistical difference, we make it converge to 0. in the time in the projection period. Maybe this, I don't know if you want to add something here, Alex.
I don't know exactly what is the leap model again.
Yeah, I'm not sure as
Statistical difference usually come when there is a different method when the supply and the demand is estimated. Now, if everything is estimated in a single model, I guess the statistical difference doesn't have really a strong meaning here. So
yeah, that's why
I guess it depends how it's estimated.
Yes, and in the WEM model, in the World Energy Outlook model, the way we treat statistical difference is that we make it converge to 0. So that's done. Next question. Sometimes the magnitudes of fuels in the energy balance table, say example oil products, are different from their individual components, kerosene, gasoline, diesel. How do we deal with these differences when modeling?
The magnitude of fuels?
You mean the share of the fuel in the total is different?
Here, the sum of oil products should match the oil product. So we do have a product which is oil products altogether, and then some subcomponents in this.
Because in the energy balances, what we showed you is the compact energy balance, but you also have the extended energy balances where you have all the different oil products separated. And this is what is used at the IEA. This is what we use when we do modeling. We don't model oil products together, but we really look at the different oil products separately. And this is what I would recommend also when modeling, to really model each fuel rather than the aggregated oil products. So again, here, I'm not sure if I understood well the question, but that's how I would see it. Let us know if it was not what you meant. So next question, for countries that do not know the calorific value, what values to use and how to estimate? You want to do this one?
So here on the default values we use, I don't know again how, I don't know exactly how those are calculated. I would point you to please send by an email if you want some more details on this. We have the relevant colleagues working on the relevant regions, and I don't know exactly how they get the data to estimate, I mean, to define those default values.
So from what I know, for calorific values, we really recommend countries to submit to us the calorific values, but sometimes this is not possible. And we use, for example, for oil products, we have some default calorific values for some regions, and for some other countries, yeah, we apply default values for other products as well. So if you're interested in having our default calorific values that we use for Ghana, for example, you can write to us, and we can share with you the information. We have a few more questions.
There is a question, yes, on the transformation efficiency of nuclear power plants.
Yeah, please.
I think it relates to the hydro and wind we just talked before. So on the nuclear power plant, here, the primary energy is not the electricity, but is the primary heat output of the reactor. So it's not the same case as in hydro here, because also this heat may be used for other purposes, namely district heating. So here, whenever the heat output is available, it can go in the balances. And the default efficiency for nuclear power plants, whenever heat is not available, is 33%. So here we do have, unlike hydro, solar PV, and wind, we do have a conversion of transformation losses. So in the conversion of heat to electricity.
Yes. There's another question. Production of oil products is captured under the oil refineries. In the transformation section, how do we capture LPG production from natural gas processing plants? Do we capture it under other transformations since it's not from oil refineries? You want to reply to this one? Oh, I could as well if you want. I think that when we, in the presentation, we focus on oil refineries, but there are several other transformation. And indeed here we have other transformation, for example, from gas to liquids plants. And this is where I think you would be reporting this.
Yes, so we definitely want to report this, but not in the other transformation transformation. But as Zakia said, there is the gas to liquid plant. We need to check exactly how the countries are reporting in, but yes, there is a transformation dedicated to that flow.
Yeah.
Again, you can have a look at the documentation.
The transformation sector, it's divided into several flows, and there are many for different transformations. You have also for coal to liquids, you have CTLs, you have charcoal production, for example, is another transformation. So yes, so depending on what you're transforming, there are the specific rows, and there are very few that would fall under this other transformation non-specified.
Yes. And there is also a natural gas liquids product itself. So if it relates to this one, so whenever available, you can have a production of natural gas liquids that can be then reallocated to LPG. So here really depends on how this product is produced. And for more details, yeah, please send an email. You can have a look more in depth.
So last question, in comparing energy balances from two different countries, is it necessary to be concerned about the methodologies in arriving at the values? And this is a big yes. It's very important, especially when you're comparing countries, to use the same methodology. And also when you're comparing values, it's quite important that you're looking at the same basis. So for example, energy balances in net calorific values, you have to be using the same physical energy content method for non-combustible fuels. We have some cases when, for example, I would say China national energy balances uses the partial substitution method, and this is different from the IEA methodology. But when we compare, then we have to adjust the balances so that we are comparing apples with apples. I don't know if you want to add something here, Alex.
No, I think you answered. The methodologies are quite different, obviously, depending on the countries, but yeah. The more we can account, I mean, the more precise the definitions, and the more we can account for what falls under this definition.
And this is where metadata is extremely important, documenting how you're building your energy balance. The more information you can provide, the more you can make sure that people are using the data in a proper way and comparing. And when comparisons are being made, it's made in a good way. So thanks a lot for all these questions. It was very interesting to exchange on this. So now let's move to the second part, which is on CO2 emissions, and I'm joined by my colleague Puya, who is an expert on CO2 emissions and who will help answer your questions after the presentation. So let me share again the presentation now. So now we will do the last part of the session, which is how do we move from energy balances to CO2 emissions. So here, Africa has been it's a minor contributor to global greenhouse emissions. during the age of industrialization. So from 1890 to 2018, Africa accounted for only 2% of global CO2 emissions. So it's not a major emitter, but climate change matters greatly for Africa. And sorry. And although Africa experiences important economic growth and energy demand growth in the IEA stated policy scenario, its contribution to global CO2 emissions rises just to around 3% of the total cumulative emissions to 2040. But Africa is in the front line when it comes to the effects of a changing climate on the energy sector. So beyond the impact on cooling needs, climate change will also lead to increasing variability in generation output, notably hydropower. So planning and investment decisions for energy infrastructure need to be climate resilient. Before we look again at the presentation, let's do some quick Menti question. I will share. So that was the last question. So please connect to www.menti.com and use the code 36, 29, 23, and 32. So the code is 36, 29, 23, and 32. And the question is, if you have your energy balance calculated with a reasonable level of granularity, can you estimate your country's CO2 emissions from fuel combustion? So here you have three possible answers. Yes, you can do it, and you just multiply the total energy consumption by a fixed conversion factor provided by the IPCC. No more information. No, you cannot do this because more information is needs to be collected. Or yes, you can use the standard IPCC carbon intensity for each fossil fuel burned in the country. So if you have your energy balance and you have a quite good level of granularity, so here what we mean is that you have the products detailed by products, the different products, can you estimate your country's CO2 emissions from fuel combustion? So most of you think that yes, you can use the standard IPCC carbon intensity, but we have a few that think that yes, you can just multiply the total energy consumption by a fixed conversion factor. So here, the correct answer is yes. If you have a reasonable level of granularity, you can use the standard IPCC carbon intensity for each fossil fuel, that is for coal, oil, and natural gas burned in the country. Next question is, among the four fuels below, so charcoal, LPG, fossil coal, and natural gas, which one is the most CO2 emitting fuel per unit of energy? Order from the most to the least emitting. So among the four fuels below, which one emits the most to the least? So here you have to rank the different fuels. Which one do you think emits the most? So here we are thinking about CO2 emissions from fossil fuel. So very good. So here the only thing is that indeed coal is the first one. It emits more than natural gas, for example. And many of you have put charcoal second, but at the charcoal is considered a renewable energy source, and at the IEA it's accounted under biofuels and waste. And so when we calculate CO2 emissions from fossil fuel combustion, we exclude charcoal in our calculation. So now let's move to the presentation. Yes, this one.
This chart represents the global CO2 emissions from fuel combustion. The share of the OECD countries in global emissions has decreased from over 55% to around 35% in less than 20 years. However, the global emissions have increased at a pace of around 2% per year, mostly driven by the emission growth in the non-OECD countries. The small blue line on top represents the sub-Saharan Africa emissions, excluding South Africa, and the orange line represents the other African countries. Despite a strong increase in the past 20 years, they correspond to only 4% of the global CO2 emissions, while representing about 15% of the global population. Credible and validated energy data are pivotal in providing high-quality emission estimations and greater confidence in the policy analysis. Access to comprehensive data enables detailed analysis of key sectors, fuels, and driving factors of emissions, both on a country-specific and global levels. This figure represents the sectoral share of CO2 emissions in the OECD, non-OECD, Africa, as well as a few African countries. The electricity and heat generation correspond to about 2/3 of global energy-related CO2 emissions from fuel combustion. Disaggregated data allows allocating the emissions associated with power generation to the end sectors and provide a more complete understanding of real drivers of CO2 emissions. The graph on the right represents the sectoral emissions after reallocation of power generation emissions to the end sectors. As you can see, in the OECD countries, buildings, transport, and industry are together responsible for about 85% of total emissions, while among the non-OECD, industry alone represents more than 50% of the total share. In the sub-Saharan Africa, however, transport remains the highest source of emissions, representing 50% of the total. Detailed emissions data enables populating matrix, which can be used to discuss the macroeconomic driving forces behind CO2 emissions and provide insightful input for effective energy and climate policymaking. The formula on the top is known as the Kaya identity, which allows decomposition of the total CO2 emissions into 4 macroeconomic factors: population, GDP per capita, total energy supply per GDP, and CO2 emissions per unit of total energy supply. As illustrated in the graph on left, among the OECD, decreasing the energy intensity of the economy alongside lower carbon intensity of the energy mix have been driving the emissions down. On the other hand, among the non-OECD countries, increase in population, GDP per capita, and carbon intensity of the energy mix have been driving upwards trends in CO2 emissions, while the reduced energy intensity is slightly offsetting this increase. In Africa, the increase in population and wealth are the main drivers of emissions increase. Most of you are perhaps already familiar with the concept of greenhouse effect. CO2 alongside methane, N2O, water vapor, fluorinated gases, and ozone are known as greenhouse gases. The greenhouse effect refers to the circumstances where the short wavelengths of radiation from the sun pass through these gas molecules, but the longer wavelengths of the re-radiation from the Earth's surface are unable to pass through them. The trapping of the long wavelength radiation leads to more heating and a higher resulting global mean surface temperature. CO2 is the major contributor to global warming, and combustion of fossil fuels is the main source of global anthropogenic CO2 emissions. The burning of fossil fuels affects the concentration of CO2 in the atmosphere. Before the Industrial Revolution, the amount of CO2 in the atmosphere was about 288 ppm. We have now reached about 414 ppm, and we are on the way to doubling the amount of CO2 in the atmosphere by the end of this century. There's currently a strong scientific consensus globally regarding the role of emissions caused by the anthropogenic activities in increasing of global mean temperature. According to the IPCC special report of 1.5 degrees C, global temperature increases by the end of the century is likely to reach up to 5 degrees C above the pre-industrial levels if the current policy trends are continued and no significant action is taken. The United Nations Framework Convention on Climate Change, UNFCCC, is an international treaty adopted in 1992 to address climate change. Starting 1995, the parties to the convention have met annually to assess progress in dealing with climate change. In year 1997, the Kyoto Protocol was adopted and established legally binding obligations for the developed countries to reduce their greenhouse gas emissions. At the 21st Conference of the Parties, or COP21, in Paris, countries approved a new global climate change agreement, the famous Paris Agreement. The aim is to limit the global average temperature increase to well below 2 degrees C, with efforts to limit this further to 1.5 degrees C. The Paris Agreement was adopted in 2015 and came into force in 2016, with 187 countries ratifying it. In COP26, which is planned to be held in November this year, countries are expected to communicate or update their national climate targets. The IPCC, with the help of IEA, has developed and refined an internationally agreed methodology for the calculation and reporting of national greenhouse gas emissions. The guidelines is called the 2006 IPCC Guidelines for National Greenhouse Gas Inventories Reporting, which is caused and used by the countries to report their emissions to UNFCCC. The IEA estimates of CO2 emissions are based on this credible international methodology. It's important to note that according to the IPCC guidelines, countries report their emissions under 5 different categories, as listed on the page. IEA deals with category 1, which corresponds to energy-related emissions only. Moreover, the energy-related emissions are divided in 3 subcategories under the guidelines. And the IEA estimates cover category 1A, which corresponds to the CO2 emissions resulting from fuel combustion of fuels only. However, as shown by the graph, energy is at the core of the greenhouse gas estimation, and the CO2 emissions from fuel combustion, which are covered by the IEA analysis, correspond to around 3/4 of total global greenhouse gas emissions. IEA CO2 estimates are based on globally recognized guidelines throughout the process. Our data collection process starts at the country level from national statistical or energy offices, where we collect energy data in physical units in the form of IEA energy statistics, which you are by now familiar with. From there, and based on the international recommendations for energy statistics as published by UNSD, and with the help of the net calorific values for various fuels, this information is put together in energy terms and forms the IEA energy balances, as it was discussed in detail earlier today by my colleague. Finally, and with the help of the default emission factors and methodology provided by the IPCC guidelines, IEA CO2 emissions are estimated. It's important to note that the IEA estimates of CO2 emissions from fuel combustion are a global database obtained following harmonized definitions and comparable methodologies across countries. However, they do not represent an official source for national greenhouse gas inventory submissions to UNFCCC. The IEA uses the simplest, the Tier 1 methodology to estimate CO2 emissions from fuel combustions based on the IPCC 2006 guidelines. Based on the Tier 1 method, the CO2 emissions from fuel combustion for a given fuel are calculated by multiplying the amount of fuel consumed in energy terms by the default fuel-specific emission factors provided in the IPCC guidelines. The computation follows the concept of conservation of carbon, which assumes that all carbon contained by the fuel burnt is oxidized and emits CO2. Emissions are then summed across all fuels and all sectors to obtain the national totals. It is also important to note that various fuels have different emission factors. For example, as you can see on the graph, combustion of a unit of a carbon-intense fuel such as a blast furnace gas corresponds to around 5 times of CO2 emissions comparing to when the same amount of natural gas is combusted. And now to conclude, there's a scientific consensus regarding the role of anthropogenic CO2 emissions in increasing the greenhouse gas concentration in the atmosphere and the global warming. Effective emissions mitigation requires collaboration on a global level, and up-to-date and accurate information on greenhouse gas emissions are essential for effective climate policy making. And most importantly, the greenhouse gas emission estimates are only as good as the energy statistics which underlies them.
So I hope that this presentation on CO2 emissions has helped you understand a bit more what we are doing at the IEA. So we have Puya with us now to help answer questions on CO2 emissions. Hi, Puya.
Hi, Zakia. Hello, everyone. I'll be happy if there's any questions.
Yes, just drop it in the Q&A box. For the moment, I don't see any questions. Please do not hesitate to send us your questions. I hope that you have understood how we use the energy balances data, and by applying the IPCC guidelines and the methodology, how do we get to the CO2 emissions numbers. I mean, I would be interested in knowing if some of you are doing this calculation for your country, or are you using this kind of information as well in your work?
Yes, I'm also interested, like with the COP26 already also scheduled later this year in November, and the massive wave of various net zero commitments announced by governments around the world and also corporations. It's interesting to know like how familiar are you with the concepts of estimating emissions and all that, because obviously provides a backbone of how we can manage our emission reduction targets.
No questions? So there's one in the Q&A box that arrived. Is carbon sequestration accounted for in the energy balance?
So here at the IEA, I think, as you saw in the presentation, we only deal with the category 1A of emission reporting under the IPCC guidelines, which corresponds to emissions from fuel combustion. So not even all the energy related emissions. So our estimates exclude the fugitive emissions from the energy industry. The carbon sequestration, the natural one, which I'm assuming that you're referring to, these are all covered in the sources and sinks of greenhouse gas emissions under category 3, which is called the agriculture, forestry, and land use category. So essentially there, which is outside the scope of the IEA, you do estimate the carbon stock change in various biomass, soil, dead organic matter, and all that. And the sequestration of carbon naturally is also included there. And if you're referring to carbon sequestration using technologies like carbon capture and storage, that just, if that technology is in place, then obviously the emissions from that are excluded from our estimates if it comes from the energy industry.
Thanks, Puya. Please, we have a bit of time, so if you have more questions, do not hesitate. No questions? Well, if we don't have any more oh, there's one. How to estimate fugitive emissions?
That's an interesting question. So based on the IPCC guidelines, the easiest method to estimate fugitive emissions, which mostly come from the energy industry, is a tier 1 method, which again, similar to the fuel combustion emissions, there are default factors provided in the guidelines for various sectors. And these factors can, for example, applied to the production from the coal mines, or the based on the capacity in the oil and gas pipelines and the oil and gas production facilities, and provide a very broad estimate. But nowadays, there's also more comprehensive methods for estimating fugitive emissions, which includes using satellite techniques and satellite data. And based on that, coming up with estimates for production-specific and country-specific emission factors. And with that, those factors are applied on the activity data from each country based on production-specific sites to come up with the total fugitive emissions from both the oil and gas and also coal industries. So it's a new field, and there's a lot of research also going on, but the satellite data have been really useful.
Thanks, Puya. Do you have more questions? Please send us now. So there's a question. You mentioned that charcoal was not included in your calculation for CO2 emissions because it's considered as biofuel. Shouldn't that be measured with whether trees that are cut down to produce charcoal being replaced by new plants? Because in my opinion, if the trees are not replaced, then they should be added.
That's a very important question. And So the way the IPCC guidelines deals with the sustainability of biomass burning, including it in the emissions or not, is actually in category 3. So in category 1, which we discussed, and it includes the emissions from the energy industry, the emissions associated with biomass and charcoal consumption for combustion for energy producing purposes are excluded. However, under category 3, which is again called the agriculture, forestry, and land use category, this, which you said, for example, sustainability of harvesting trees and how that is impacting the carbon stock change is included. And if the charcoal production or wood chop production and all that are happening in an unsustainable way, that will be implemented in the emissions associated with that category.
Yeah, thank you. Any more questions before we move to the exercise? No more questions? Then thanks, Puya, for joining for the question and answer. And now let's move to the...
Thank you, everyone. Have a nice day.
Thanks, Puya. Bye.
Bye-bye.
So for the exercises on balances and CO2 emissions, I hope that you have been able to take a look at the exercise and try to answer them. So the first question was, you are asked to fill out this energy balance, which was incomplete. And the first question was, why coal and electricity plants? So why is the coal used in electricity plants C11, cell C11, and crude oil in refineries, so crude oil input to refineries, negative. So this is what we have seen during the presentation. In the transformation sector, we have a sign convention where inputs are reported as negative. And why is oil products refinery a positive number? So oil products refinery, which is cell F12, why is this a positive number? And the answer is because it's an output to the transformation. The second question is, using the results from the exercise 1, complete the simplified balance here for the year 2019. You need to complete the natural gas balance and report also hydro, solar PV, and wind. And here we are using net calorific values. So here note the units, it's terajoules in net calorific values. And for hydro, wind, and solar PV, we have to use the efficiency, the proper efficiency. So let's look at natural gas. So here, I don't know if you remember, but in the exercise here yesterday that we looked, so here for the year 2019, here you will link it to this one and this one here, which is in terajoule gross calorific value. So here you will multiply it by 0.9 because that's the conversion from gross to net. There's 10% difference. So same for imports, everything you will link to that table here. So for natural gas, it's easy. Then for electricity here, you will link to the table on electricity here. So for 2019 coal, it's 688. So here it's in gigawatt hour. Here also the unit, it's gigawatt hours. So it's just an equal to that number there. So with this, you will be able to compute all this, and this is just the sum. Once you have computed you have added your hydro, solar PV, and wind electricity generation. As we said, for them, it's 100% efficiency. So you can calculate your electricity plant's input. And but here the electricity plants, it's in terajoules. So you have to convert the output into terajoule using this conversion factor. So 1 gigawatt hour, it's 3.6 terajoule. And here, because it's an input, you will put the negative sign in front of your output. So you will have your numbers here. And for electricity here, it's just the total electricity generation. So here also it's the same, but in different units. So here you just convert it to terajoule. And for production here, it's just the amount of input, but you remove the negative sign because it's exactly your input here. So that was it for this. The question 3 is, looking at refinery transformation, do you see anything wrong? Why? So how do we calculate your refinery efficiency? It's your output divided by your input. You remove the negative sign and you get 107%. So do you see something wrong here? So yes, the efficiency is higher than 100%, and this is suspicious. So, and it's not normal because in energy terms, there should not be energy gains. In volumes, however, as I said earlier, this is possible because sometimes you can have your output from refinery higher than your input because of lower density of oil products compared to crude oil. So here, this means that either the oil products output or the input is wrongly reported, and you have to query your data provider. Is it because of some wrong calorific values? Is it because of some incomplete data observations? Are we double counting some products here, maybe in the oil products? So this is something you have to question. So the last question was, calculate the CO2 emissions for total energy supply and electricity generation for each fossil fuel and as a total. And so here, what do we do for total energy supply? So here you are given the carbon emission factor for the different fossil fuels. So it's in ton of CO2 per terajoules. And you are here to calculate it. You take your total supply value, you multiply it by your emission factor here, but here it's in kiloton CO2. So here you will, and here you're getting ton. So here you will divide by 1000. And it's the same formula for gas. You take your gas total supply, you multiply by your natural gas carbon emission factor, and you divide by 1000, same for those, and your total emissions, it's the sum of those. For electricity generation emissions, so here you would take your electricity input, you remove the negative sign again, and you multiply by the emission factor of the fuel, and you divide by 1000 again to adjust for the unit, and the sum is just the sum. So that was it. And the last question was, calculate for each fuel generated electricity, the CO2 emission intensity in gram of CO2 per kilowatt hour of electricity generated, and also the average electricity carbon intensity in the country. So here what you need to do is to calculate the electricity CO2 emissions intensity. You need to divide the emissions related to energy plants by the electricity output. And to obtain gram of CO2 per kilowatt hour, you multiply by 1000. So here what we do is that we take the emissions related to electricity generation, we divide it by the amount of electricity generation, and we multiply by 1000 to get gram of CO2 per kilowatt hour. And you do that also for natural gas. For crude oil and oil products, there's no electricity generation. And for the total, what you do is that you take your total electricity generation emissions, you divide it by your total amount of electricity output, and you multiply by 1000. So that was all for the exercise. I really recommend you to try to do it if you have not yet done it. And if you have if you want, you can also send it to me for correction by email. I will be happy to correct and see if there's something which you have not understand. I could also give you more explanations if you want. So that was it for me. There was a last question I see. How do we calculate the emissions related to international bunkers? International bunkers, I think we don't, I need to check with Puya on this one. I think we exclude it. Usually, let me check with Puya. I don't know if you have any question on related to the exercise. So yes, exactly. So for international bunkers at the national level, you would exclude it. So you would not count bunkers in your national CO2 emissions, but at the world level, you add it. We do add it when we are calculating the total world CO2 emissions, but not at national levels. So I hope that this answered the question. And if there's no other questions, then that was the last part for today's session. Yeah, so please, if you have any questions related to energy balances and CO2 emissions, even after the session, you can always drop me an email and I will be happy to reply to you. And tomorrow we will do the last part of the statistics webinars. It will be on energy prices and taxes, and also on energy efficiency indicators. And there will be 2 exercises, one on prices and one on energy efficiency indicators. If you have time to look at them before the session tomorrow, that would be great. And thank you again for listening to me during this session, and see you all tomorrow. Bye. So someone asked to send my email. I'm just writing it here. So I put it in the Q&A box. My email, it's zakia.adam@iea.org. So bye everyone, and see you tomorrow.